Welcome to this video lesson, which is the full solution to the practice questions from lesson 16, which focuses on the shortest distance between a point and a line. In this first question, we're given 3 points, A, B, and C, and for the first part, we are to determine the shortest distance from B to AC. It's good to start off these questions with just visualizing what is happening. So let's say point A is here. Point B, let's put it here. It's B, that's 301. And let's put a point C randomly. Let's put it here. And this is point 112. We want the shortest distance from B to AC. So I'm going to draw a line between A to C. It's going to go this way. And the shortest distance from B to AC, it will be a perpendicular line to AC going this way. It's going to be perpendicular, and let's say it meets here at point P, and this is going to have coordinates X, Y, and Z. We need some information about line AC, or a line that goes through points A and C. So to do that, we need two pieces of information. We need their direction vector, AC. So we can either do AC or CA, it doesn't really make a difference. To do this, I'm going to take the coordinates of C, 1, 1, 2, and subtract them by coordinates of A, which are 1, 2, 3. And when I do that, I get 0, -1, and -1. To have the equation for the line that goes through AC, I need a point. We can either use point A or point C. It doesn't make a difference. We're going to choose point A in this case, and that's going to have coordinates of 1, 2, 3, or the position vector will have components 1, 2, 3. And we're going to add this to T with some parameter multiplied by the direction vector AC, which is 0, -1, and -1. Now that I have the equation of a line passing through these two, and I also have the direction vector, I know that this vector here, BP, and this direction vector are going to be perpendicular. And since BP and AC are perpendicular, therefore BP, or the dot product of BP and AC, is going to equal to 0. Well, for BP, to find the vector for BP, we are going to take all the coordinates of X here, P here, so X, Y, and Z, and we're going to subtract them by coordinates of B, which are 3, 0, and 1. And we're going to use a dot product of that and AC. Well, we found AC already here, so we're going to use 0, -1, and -1. And that's going to equal to 0. For the dot product, we are going to take the x component, the y component, and the z component, and we're going to multiply them by each other, and then we're going to sum them all up. So for the first one, we're going to have 0 times x minus 3, minus 1 times y minus 0, and minus 1 times z minus 1. And this is going to equal to 0, and in terms of colors, this is the first row, this is the second, and this is the third. Now the first term is 0, we got minus 1 times y, which is negative y, -1 times -0 is just 0, and then I have -1 times z, which is negative z, and -1 times -1 is positive 1, and this is going to equal to 0. Now I have, if I were to rearrange this, I will have y plus z is equal to 1, and I've done that by adding y and z to both sides of the equation. So maybe I'll write that down. So add y and z to both sides of the equation. Now we have an equation here that can help us figure out what that coordinate may be, but the problem is we have two unknowns and one equation. But there is a way to link the x, y, and z value here because we know that the x, y, and z value of point P lie on the line AC. And the line AC's equation is here, and we can find the x value, the y value, and the z value in terms of t. So we're going to do exactly that. So we know that the x value is going to be 1 plus t, or 1 plus 0 times t. The y value is going to be 2 plus t times negative 1, and the z value is going to be 3 plus t times negative 1. I'm just going to write that down so we know all the values. So in pink, x is going to equal to 1 plus 0 times t, which is just 0, so I'll just leave it as 1. For y, it is going to be 2 plus t times negative 1, so that's negative t. And I have z is equal to 3 plus t times negative 1, which is 3 minus t. Now I can use this to find the value of t here. So we don't have x here, so I don't have to plug anything in here. The y value here is 2 minus t. So we get 2 minus t plus the z value, which is 3 minus t. So 3 minus t, and that's going to equal to 1. We're going to simplify this. We're going to have 2 minus t plus 3 minus t is equal to 1. 2 plus 3 is 5. Minus negative t minus t is minus 2t. That's going to equal to 1. I'm going to subtract 5 from both sides. I'm going to get negative 2t is equal to negative 4. And I'm going to divide both sides by negative 2 to get t is equal to 2. Once I have the t value, then I can start finding the x, y, and z value. I know that for my line here, the x value is always equal to 1. So that value is constant and it's not changing. The y value is 2 minus t. So I'll write them down here. I'm using this information here. So x is equal to 1. Y is equal to 2 minus t. So that's 2 minus 2, which is 0. And z is equal to 3 minus t. So that's 3 minus 2. And I'm getting a 2 from here. And that's equal to 1. So the point of intersection P here is equal to 1, 0, 1. And that is the foot of the perpendicular to the line here. So that means that the x value here is 1, y is 0, and z is 1. And this point will be the point which is the shortest distance from B to this line over here, line AC. So now that I have the point, I can find the vector BP. Vector BP is going to equal to, I'm going to take all the coordinates of P, 1, 0, 1, and subtract them by all the coordinates of B, which are 3, 0, 1. And this is going to give me negative 2, 0, and 0. Interesting. To find the shortest distance, we need to find the magnitude of this vector here. So that's just going to be the magnitude of BP. That means we are going to take the root of the x component squared plus the y component squared plus the z component squared. This is going to be root 4, which is going to be 2 units. And that is the shortest distance from B to AC. So let us highlight this information, and we are going to use a highlighter to show our final solution. The next question, or part B, says, hence, determine the area of ABC. So ABC actually is, I'm going to connect them here so you can see it. It's actually a triangle. And for this triangle, we have a base here. Our base is going to be AC, and we've already found the height of our triangle. And this terminology here, hence, says to use the information from part A or previous parts to answer the question. So if you are taking this course in the IB curriculum and whenever you see hence, you have to use this information that you found from the previous question to answer it. There will be times where the question says hence or otherwise determine the area, and that will allow you to use this information or any other methodologies or procedures to solve the question. But since this one says hence, you have to use the information from here. Well, in this case, it is easy to use the information from the previous question because we know the height of our triangle here is 2, and all we need to do is find the base, which is the magnitude of vector AC. And once we have the base and the height of the triangle, we can find the rest of the information, or just the area is base times height um, divided by 2. So let's bring the page up a little bit. Actually, I'm going to bring it up right to here first. And we are going to redraw this. This is going to be part B. We're going to have a triangle. I'm going to draw it in a, oh, well, I can draw it in the same orientation. I got B, I got C here, and I got A here. And I'm going to label this one as 1, 2, 3. Label this one as 1, 1, 2. And this one is going to be 3, 0, 1. And we already have the height of our triangle at magnitude of 2. I'm going to shift everything up here. Now, I need to find the base. The base is going to be the magnitude of vector AC. So, magnitude of AC. And we have found vector AC in the previous part of the question as well to be 0, -1, -1, or you can just multiply it by -1 to get vector CA. Doesn't really make a difference. For the magnitude, it's going to be the root of x component squared plus y component squared plus the z component squared, and this is going to be root 2. Once I have the, and sorry, this is going to be 2 here. So now to find the area, area is going to equal to base times height divided by 2. My base is root 2, my height is 2, and I'm going to divide it by 2. The 2's are going to cancel, and I'm going to have my area as root 2 units squared. And that's going to be my final answer here. For the second question here, we are given that two boats have position vector r1 and r2, and we want to determine part A of the question, the speed of each boat. Well, we have the equation here, and in the equation, this is the starting point of the boats. This is the time it takes that is traveling in a certain direction, and this is its velocity. Well, for part A, the speed 1 is going to equal to the magnitude of the velocity vector 1. Velocity vector 1 is this one over here, and velocity vector 2 is the one here. So this is going to be v1, and to find this is the root of the x component squared, which is -1 squared, plus the y component squared, which is 2 squared. So this is going to be root 1 squared is 1 plus 4, so this is going to be root 5. I've definitely forgot to give you units for this. Let's call this kilometers, and let's imagine that velocity is given in kilometers per hour. So in this case, our unit for this is going to be kilometers per hour. For speed 2, or for r2, we're going to look at the velocity 2 or its magnitude, and that's going to be the root of the x component squared plus the y component squared. When we do this, 3 squared is 9, and 2 squared is 4, so we're going to have root 13 as our final answer, and that's going to be in kilometers per hour. The second part of the question asks us at which time are the boats closest to each other? This is a challenging question. This is different than what we've already done because usually what we do is we look at the shortest distance between a point and a line, and that happens when the two are perpendicular. But in this case, we have two lines that have their own equation. And let's draw this out to get an idea about how it's going to look like and see whether or not we can find another method of figuring out the shortest distance. Let's start off by drawing out the situation. So I am going to draw a grid, and let's draw it this big. And we are going to start with the first equation. And in our first equation, our starting point is 3, -4. So 1, 2, 3, 1, 2, 3, 4. And every hour we move by -1 and 2. So -1 to the -1 means 1 to the left, and 2 up means in this direction. So after the first hour, we're going to be here. After the second hour, we're going to be here. Third hour, fourth hour, and fifth hour. And if we were to connect this, it will look something like this. And again, this is t1, this is t is equal to 0, this is t is equal to 2, this is t is equal to 3, t is equal to 4, and t is equal to 5. For the second one, let's use purple. And our starting position is 4, 3. 1, 2, 3, 4, 1, 2, 3. That's here. I'll write that out. This is 4, 3, and this was 3, -4. So this is our position at time is equal to 0. And we move by -3 in the x direction and -2 in the y direction every single hour. So after the first hour, we move 3 to the left and 2 down. So we're going to be here. After the second hour, we are going to move another 3 and 2 down, and then we're going to do that again over and over again for the next little bit. So t is equal to 1, we're going to be here. T is equal to 2, we're going to be here. And t is equal to 3, we're going to be here, and so on. So I'm going to connect these using a line. And we're going to keep moving this way as time passes. Now, when we are trying to figure out at what time they're the closest to each other, you might think that it will happen when at the point of intersection, and that is not true because at point of intersection is just saying that at some point, if this boat here left the trail and this one left the trail, at some point their trails will meet. It has nothing to do with their current position. At time 0, their distance is here, so that's a pretty long distance. At time is equal to 1, their distance is going to be this distance over here. At time is equal to 2, their distance is going to be this distance over here. And time 3, their distance is going to be this distance over here. So you can see that their distance is large at first. It starts to get smaller, and then it gets bigger again. So somewhere between time 1 and time 2 might be the shortest distance. Note that their distance is no longer a line that is perpendicular. So usually we would take this point and we would look at the perpendicular to this line, but that doesn't tell us anything in this case because it's not a fixed point. The point keeps moving. So the initial distance is here, then here, then here, then here, and so on. So how do we find this distance? Well, this distance, at time is equal to 0, our distance is going to be from here where they start, and that's the length of it. So this displacement will have an x component here, and it's going to have a y component here. The y component is going to be this y value minus this y value, so that's delta y, or y2 minus y1. And this one over here is going to be x2 minus x1. This is going to be the same at every time period. So at time is equal to 1, we're going to do the same thing. This is going to be the change in x. This is going to be the change in y, and so on. And to find this distance in between, since we have the x component and the y component, we can use the Pythagorean theorem. So I'm going to say that this is the distance, and the distance squared is going to equal to the x component here, this one over here, which is x2 minus x1 squared, plus the y component of this. And we know this angle is 90 degrees here, so we can use the Pythagorean theorem. And this is going to be y2 minus y1 squared. And to find the distance itself, I'll start writing in black again. Distance is equal to, we are going to take the root of the x component squared plus the y component squared. Note that if this was in 3 dimensions, you would do x component squared, y component squared, and z component squared, and you would arrive to the same solution. But the distance is going to be this over here. And we do have an expression for x2. That's 4 plus t times negative 3. We have one for x1. That's 3 plus t times negative 1. And we got an expression for each one in terms of t. And we can use that idea to find the shortest, or the time at which the distance is shortest. Okay, let's try this out. I'm going to say this is going to equal to, and I'm going to start my roots. And for x2, x2 comes from equation 2's x component. So I'm going to label that here. I'm going to do it with purple. So that's going to be this one over here. And that's going to be 4 plus, and that's t times negative 3, so that's negative 3t. So that's this one over here. And then we're going to do x1, which is going to be this component, and that's going to be minus, I'm going to put it in brackets, it's going to be 3 plus t times negative 1, so that's 3 minus t. And then we are going to square all of this. I'm going to do this like this. And this was the x1, and everything is squared. That's this component here. And then we're going to do the same thing to the y value. So this is going to be plus, and let's use, for y2, we're going to use purple again. That's this component over here. That's 3 plus t times negative 2. So that's 3 minus 2t. And for the pink, for y1, it's going to be negative 4 plus t times 2, which is going to be plus, actually minus, in brackets, negative 4 plus 2t. And we need to square this, and we need to take the root of all of it. Okay, next thing we are going to do is we are going to simplify the brackets a little bit. We are going to have 4 minus 3t. I'm going to expand this bracket and this bracket here. So the first one is going to be minus 3. Negative and negative make it positive. And we are going to have 3 minus 2t. Negative times negative is positive 4, and negative times 2t is negative 2t. and this is squared as well. We keep going. We are going to have the square root of, and we are going to simplify this and this. For the first one, we have 4 minus 3, which is 1. We got a negative 3t plus t, which is negative 2t. This is squared. And for the second bracket, we have 3 plus 4, which is 7. And we got negative 2t minus negative 2t, which is negative 4t squared. Okay, we are going to continue down here. So I'm going to shift everything up. And I'll write it here. We got d is equal to, we got square root. And now I'm going to expand this. So I'm going to use the squares. So we got 1 minus 2t squared. That is going to equal to 1 minus 4t minus, or plus 4t squared. And we are going to have plus 7 squared is 49. Negative 4 times 7 times 2, that's 28 times 2, which will give us negative 56t. And we got negative 4t times negative 4t, which is plus 16t squared. And I'm going to use this. And finally, I am going to not finally, but next step is to simplify. So we got 1 plus 49, that is 50. We got negative 4t, we got negative 50/60, that is negative 60t. And we got plus 4t squared plus 16t squared, which is plus 20t squared. And this is going to be our distance value. And you can see that our distance is obviously it's a root here, but it is quadratic function over here. And this quadratic function can be simplified, so let's do it. Let's divide everything by 2, and we're going to get 25 minus 30t plus 10t squared. Or we can rewrite this. We're going to take the root 2 out, and we are going to have a root of, and I'm just going to rearrange in good form. We're going to have 10t squared minus 30t plus 25. So I just rearranged everything here. The root 2 came out. I brought 10t squared first, negative 30t, 25 here. Now our distance here is going to be basically because we have this quadratic function here, and our quadratic function is one where it opens upwards because we have our coefficient of t squared, or let's say x squared, is positive. So we know that our graph is opening upwards. And basically, that is telling us, and that's a good sign, because if it opens upwards, we know that based on our graph, basically at time 0 the distance was high, the distance started getting low, and then it became the distance started increasing between the two boats afterwards. So we need to find that minimum distance point over there. And we can either do this using a graphing technique. So we can just, if you have this on a test situation where you can use a graphing calculator, then all you have to do is graph this function. And once you graph the function, you will get something like this. I'm going to draw it out. And you can find your minimum point here, and this is the t and distance graph. So this value over here would be your, so that's the minimum of your quadratic. That's going to be your minimum. And when we do this on a calculator, we will get a value of 3 over 2, or 1/2 is our minimum. And we can also find the distance value as well. We will find it to be 2.236 approximately, or 2.24 in 3 significant figures. So if you have a calculator, once you reach this Actually, once you reach this location, right away you can plug it into your calculator and find that the time and the distance, which is the next question. If you didn't have your calculator, then you have to use this quadratic to find this minimum point. Since we know it's a quadratic going this way, we can find the minimum point using the equation where the vertex of our value, so the vertex is going to equal to negative b over 2a. Our a value here is 10, that's a. Our b value is negative 30, and our c value is 25 for our quadratic. So plugging that into our equation, we get negative 30 over 2 times a, which is 10. And the negatives cancel, and we're left with 30 over 20, which is equal to 3 over 2, which is consistent as to what we would get when we used our calculator. So therefore, because of this, the time for the minimum distance is 3 over 2 hours. Now part C asks us to find the minimum distance, and basically we've found the minimum distance here. If we had used our calculator, we could just read it off the graph, but we can find it if we did not have a calculator, and if we had to find the quadratic using using the quadratic formula, then we would find this. And I'm just going to zoom up or just scroll up a little bit. For part C, we know that our distance formula is equal to root 2 times the root of 10t squared minus 30t plus 25. And we know that minimum distance is at t is equal to 3 over 2. So we're going to plug that into our equation. We're going to get root 2. Here we're going to get 10 times 3 over 2 squared minus 30 times 3 over 2 plus 25. This is going to turn to root 2. We are going to have 10 times 9 over 4 minus 30 divided by 2, which is 15 times 3, which is 45 plus 25. And I'm going to scroll up a little bit again. We are going to do root 2 here, and right here what we are going to do, we're going to write everything as a division by 4. So we're going to have 90 in the first one minus 180 plus 25 times 4, which is 100. Now this would be root 2 over here. We have our denominator is root 4. So we're going to take that out. So this is going to be root 4. And on our numerator here, we have 90 minus 180 plus 100. So 90 plus 100 is 190. Subtract that by 180 and we get root 10 up here. We are going to simplify this further. So on the numerator here, we're going to have root 2 times root 10, which is root 20. And we are going to divide it by root 4. That's same as root 4 times root 5 over root 4. And the root 4's cancel out, giving us root 5 as our final answer. So that's the distance. That's the minimum distance between the two boats, and that happens at time is equal to 3 over 2. So I guess this question could be done using it. If it was done using a calculator, then just plot that equation in and find the time and the distance right away. It's quite easy that way. But if you do not have a calculator, so for example in IB's paper 1 type questions, you would have to go through this process and actually simplify your answer to root 5 kilometer. I hope that this video was helpful in giving you some practice for the shortest distance between a point and a line. I know the second question was much more challenging and it involved you folks to find the distance or the shortest distance between two lines, but I think it was a very useful practice, and I hope that after completing it, you have a much better idea about how you can solve these types of questions. Thank you for watching.